This video we're going to look at logarithm 1. This aspect of logarithm deals with applying the relationship between indices and logarithm and laws of logarithm to solve problems. So here we will not use log tables. In logarithm 2, I'm going to teach you how to solve problems using log tables, but in this class on logarithm, it's just going to be about relationship between indices and logarithm, and that means that we're going to know, or we need to know, the laws of logarithm. And for you to appreciate the laws of logarithm, you also need to know fundamentally the laws of indices. So I have a playlist on the laws of indices, everything about indices. So I would want you to pause this video and watch that videos on that playlist first if you are new to indices, or maybe you want to grasp the laws of indices, the laws that govern indices, so that by the time we apply them in logarithm, it will not look strange or it will not look difficult for you to understand. So you can just go to the channel. If you have not subscribed, just subscribe so that you can have access to those videos in that playlist. All right, let's begin. So logarithm 1, this aspect of logarithm deals with applying the relationship between indices and logarithm and laws of logarithm to solve problems. So here we are not going to use log tables. Relationship between indices and logarithm. So if b raised to the power x is equal to n, then x is equal to log n to the base b. Now this is index notation or indices notation. So in indices, b raised to x equal to n, it implies that whenever b, which is the base, is raised to a specific power, it will give a number, b raised to x equal to n. For instance, if 2 raised to the power 4, what would it be? So 2 raised to the power 4 implies that 2 will repeatedly multiply itself 4 times to give what? 16. So 2 raised to the power 4 equal to 16. That's understandable. So it's a shortened way. 2 raised to the power 4 is a shortened way of writing 2 times 2 times 2 times 2, which is equal to 16. Rather than writing 2 times 2 times 2 times 2 to give you 16, we just write 2 raised to the power 4 equal to 16, which is still the same thing. Both of them are the same thing, just that this is a shortened form of this, and this notation is known as index notation. So that was what I was referring to earlier, that I have a series of videos on indices which you need to watch for you to understand it, because we're going to apply basically the rules or laws that govern indices here, because this part of logarithm is especially relationship between indices and logarithm. So the laws that apply to indices are definitely going to apply to logarithm in this class and onwards as we treat logarithm 1. All right, so take note of that. Now, so if b raised to the power x is equal to n, then x is equal to log n to the base b. Now note, students should observe that both indices and logarithm make use of the same base when we are converting from one form to another. So in indices, 2 raised to the power 4 is equal to 16. So 2 is known as the base, and then 4, which is what 2 is raised to, is known as power, or the power, or exponents, or index. Now, what it implies that when 2 is raised to the power 4, the result is 16. Now, if you represent this in log form, this relationship, this notation in logarithm form is going to be this base, that will be log 2 16 is equal to 4. So that tells you that the logarithm of 16 to the base 2 is equal to 4. So this is a relationship between the index notation or indices and logarithm. Both of them share the same base. So here in the indices, the base is 2. Here in logarithm, the base is also 2. So take note of that. So let's move on to examples on simple applications. Number 1, or number figure 1 rather. Given that 10 raised to the power 2 is equal to 100, write the expression in logarithmic form. So 10 raised to the power 2 is equal to 100. Now, to write this in logarithmic form, this 2, which is the power, will be here. First of all you need to do is to bring the write your log elsewhere. So I think that's what I did here. Okay, no, this is so 2 there are 10. Just write a log So convert, assume I'm doing it here afresh. So let's say 10 raised to the power 2 is equal to what? 100. So to write this in log form, then you say log 100, this to the base 10, so the 100 is equal to the power. So that's just all you need to do. So all you need to do is just logarithm of 100 to the base 10 is equal to the power 2. So that's just the relationship between indices and logarithms. So take note, both of them have the same base. Here the base is 10 and here the base is 10. Same thing applies in the rest examples. So if 2 raised to the power 6 is equal to 64, write the expression in logarithmic form. Write the expression in logarithmic form. So 2 raised to the power 6 is equal to 64. So logarithm of 64 to the base 2 would give us the power 6. Here is power. Here 6 is the power, so which 2 is raised to. But in log form, 6 is the result of log 64 to the base 2. Now, number 3, express 4 raised to the power x equal to 256 in logarithmic form. So 4 raised to the power x equal to 256. So x, which is the power, become our result equal to log to the base 4, 256. So don't look at logarithm of 256 to the base 4 is equal to x. So number 4, write in logarithmic form. 7 raised to minus 2 is equal to 1 over 49. So of course this will give us so our base, our power here will become our result, or we can start by saying log. Now the result in index notation, this is equivalent to 149. In logarithmic form, this answer is what I'm going to write here, 1 over 49. Then the base here in index notation is what you are going to have as a base in our log notation. Then the power here is equal, will be our result, minus 2. So that's exactly what you have here. So log minus 2 is equal to logarithm of 149 to the base 7. So basically that's how you convert from indices to logarithm, or you convert from index notation to logarithm. Next, we move on to laws of logarithm. Just as we have laws of indices, so also do we have laws of logarithm. And it's essential that you know and understand and should be able to apply the laws of logarithm when needed. So number 1, the first law is that of multiplication. So logarithm of mn to the base b is equal to log m to the base b plus log n to the base b. So whenever there's multiplication, we add the there's addition when there's addition in respect to the two numbers that were multiplied on this side. So mn multiplication here, but when trying to get the solution, you add you have the values here, their respective log to the base, so the respective base individually. So log mn to the base b is equal to log m to the base b plus log n to the base b. So that's what it implies. So examples on simple applications: log 30 to the base 6 is equal to log 6 times 5 to the base 6. So what you do is that you get to find two numbers that when multiplied gives you 30. So that gives you, so with that you can get the sum of those two numbers and to the respective sum of those two numbers, so base 6. So log 6 times 5 to the base 6 equals to log 6 to the base 6 plus log 5 to the base 6. So this is the what you have here is as a result of the multiplication law of logarithm, which gives this part. So once you have something like this, you can simplify it in this form. Same thing applies here. Log 72 to the base 2 will give us log 8 times 9 to the base 2. So this gives us log 8 to the base 2 plus log 9 to the base 2. Then log 3, log 9 to the base 3 plus log 27 to the base 3 Now on this side, once there's addition, so you carry out, you know that multiplication gives you addition, so addition will give you multiplication. So it's still the same thing. So now that you have addition on this side, that means that it will not be log 3, then 9 times 27. So the log values will multiply themselves to give you the total value. So now that you have addition on this side, to simplify this, you need to multiply this 9 times 27 to the base 3. So that's what you have here, 9 times 27. The 9 times 27, which is what you have here, will give you this addition, which is what you have here. So that's what it implies. So this now gives us log 243 to the base 3. 243 is gotten from 9 times 27. So this is exactly from here. It's as if from here, when we have log 30 to the base 6, we have to look for two numbers, and when multiplied, give us 30. And then from there, so those two numbers when multiplied now give us multiplication, where we need to apply the multiplication law of logarithm, which now gives us log 6 to the base 6 plus log 5 to the base 6. So exactly what you have here. 243 is from 9 times 27. So this, when simplified, when applying the multiplication law of logarithm, you're going to have this addition of it, so which is log 9 to the base 3 plus log 27 to the base 3. But take note, when you have log 9 to the base 3 plus log 3 to the log 27 to the base 3, don't add. Don't be tempted to add, like, because when you go to this point you added, and also when you go to this point you added. So of course, since there was no multiplication, you should just do or follow suit. No, don't be tempted to add 9 to 27. Rather, multiply. The law says when there's multiplication you add, and when there's addition you multiply. So that's what you should do. Number 2, log n raised to the power k to the base b is equal to k log n to the base b. So which means that the logarithm of n raised to a specific power it's also equal to that power multiplying log n to the base b. So examples on simple applications is log 100 to the base 10 is equal to log 10 to log 10 raised to the power 2 to the base 10. So this means that we can write 100 in index notation. So once we can do that, this 2 will multiply. We bring 2 backwards, so that 2 multiplies logarithm of 10 to the base 10. So this is what you're going to have. Eventually you get to know that any logarithm of any number to that same base, it will give you 1. So for instance, log a, so a is equal to 1, log 100, so this 100 is equal to 1, and log 10, so 10 is equal to 1. So logarithm of a number to that same base, so the base of that same number is equal to 1. So log 10 to the base 10 is 1, so 2 times 1 is equal to 2. But for now, just leave it like this. As we take examples after this part of the lesson, we're going to simplify it further to this point. So same thing applies there. So now take note, just as we did here, okay, this particular example, usually we said that multiplication, when you have multiplication, this will be the result. So the law of multiplication results to addition of the logarithm of each of the numbers that were multiplied. But if this is what is given to you, then you can from here get this part, just as initially we got log 30, log 72, we have to multiply and then go to this point, But in this case, it was log 9 to base 3 plus log 27 to base 3 addition, then we multiply, we go to this point. Same thing with this same law. When it was here is we needed to in this case, log 243 to the base 7 is equal to log 7 raised to the power 3 to the base 7. So since 7 is now, we can write 243 in index notation, and the power can multiply. The power will be brought backwards. Not that it has to be brought backwards. So which is what we did here, 3 log 7 to the base 7. So just once you can write a particular logarithm in an index form, or in an index form, the power will be brought backwards. So 10 raised to the power 2, you bring the power up here. Then 7 raised to the power 3, you bring the 3 backwards. So that's what you're doing. But now look at it. In this case, the power is already at the back of or behind log 25 to the base 5. So what you do, you bring it back, and then if it will be equal to this form where 25 will be raised to 1 over 2. This 1 over 2 was what was brought backwards, just like just as this law states here, that when n is raised to power k, you bring the power back, and then you have log n to the base b. So if from here you get this form, and then from here you get this, just as from here you get to this point, and from this point you also get to this point. So that's what it implies. Then let's look at special cases under this particular law. Now, logarithm b to the base b is equal to 1. Take note of that. The logarithm of any number to its base is 1. So logarithm log b to the base b is equal to 1. How? Now, in index form, log b is raised to 1. So if you bring the 1 backwards, you're going to have 1 log b, logarithm of b to the base b, which is equal to 1. Why is it so? Because b log b to the base b is equal to 1. That was what I explained here. Anytime you have the logarithm of a number to the base, to its base, say log a to a, that's already 1. Log 100 to 100, logarithm of 100 to the base 100 rather is equal to 1. And logarithm of 10 to the base 10 is equal to 1. So whenever you come across any log that's in this form, it could be any number, it could be anything, but as long as it's the logarithm of a number and the base is still that same number, then automatically it's equal to 1. So the rule is any logarithm to its base is 1. Then the second special case we're going to look at is log 1 to the base b is equal to 0. Why? Because log 1, you can only get 1 from our index notation, from indices. Any number raised to 0 is equal to 1. So of course 1 here implies that the number is raised to 0. So logarithm of log b raised to power 0 raised to b is equal to 0. Why? So this 0, since it follows this notation, log n raised to power k to the base b, so now log b raised to power 0 to the base b. So this 0 brought back was, to which now in this form here, rather 0 times log b to the base b. And remember, log b to the base b is 1 from what you have here. So 0 times 1 automatically will now give you 0 times 1 is equal to 0 rather. So that's why log 1 to the base b is equal to 0. So the rule is that logarithm of 1 to any base is 0. So that's the second law. Now let's look at the third law, which is the law of division of logarithm. So log m divided by n to the base b is equal to log m to the base b minus log n to the base b. So when there's division, you subtract. When there's multiplication, you add. Remember from the laws of indices, when indices are multiplied, you add, and when they are divided, you subtract. So that is carried over to logarithm also. So for logarithm, when there is multiplication, you add, and when there is division, you subtract. So logarithm log 36 over 17 to the base 6 is equal to log 36 to the base 6 minus log 17 to the base 6. Same thing here, log 100 over 3 to the base 10 is log 100 to the base 10 minus log 3 to the base 10. And similarly now, this log 81 to the base 3 minus log 9 to the base 3, don't subtract because we already have subtraction here. That tells that for subtraction to be here, it means that there was a division on the other side. So which means log 3 bracket open bracket 81 divided by 9, which is what we have here. So it's exactly what I explained here. For you to have addition, it means that there was for you to have addition on this side, it means that there was multiplication here. And same thing here, for you to have 1 over 2 at the back of this expression, log 25 to the base 5, it shows that 25 was raised to 1 over 2 initially for you to get this. So which means if we have this form, we can have this part here. So both of them are equal. So same thing here. Once you see subtraction like this, log 81, or it could be log anything, but subtraction between the two expressions, you can express it in this way. So both of them are equal. With these laws, we are going to proceed to taking examples on logarithm 1.